So I'd like to talk about semantic parsing of English to GraphQL. So first of all, a little bit about GraphQL for those that don't have too much of a background. GraphQL is basically a query language for your API. This can be compared to SQL, which is a query language to databases. GraphQL can cover a whole API, which means it can cover a broad set of business logic, databases, and data types. One of the strengths of GraphQL is its ease of developer use. It lends itself well to nested relations. It provides a schema which serves as an API contract, and it can make the development experience for software engineers a little bit easier. So here we can see a little bit about what GraphQL looks like. GraphQL lets you describe your data in a schema. And here you have a small example of that. It can show you the relationships between different types of data. With that schema, we can send a query, and that query can give us a predictable result of exactly what we expect to receive from this interface. Semantic parsing is the task of converting a natural language utterance to a logical form, a machine understandable representation of its meaning. In this case, we're converting English natural language to GraphQL, which is the logical form or the machine understandable representation of its meaning. So here we can see a little bit more of what this looks like. So for example, if we have some English prompt and English natural language, such as what is the name and date of the song released most recently, and some GraphQL schema that defines that data, we can find the corresponding GraphQL query, such as this. So why did I want to go through this project? There's a few reasons. The first of which is I wanted to understand the limits of general language models for semantic parsing. This task is a little bit similar to machine translation, wherein we take some input language and output a target language. In our case, we're inputting English and outputting GraphQL. I wanted to see how it could potentially ease the learning curve for developers. So if a developer has the ability to interact with a model that generates queries for them so that they can see how these queries are structured, it might make it easier for them. And finally, this could be potential tooling for non-technical data users. So an example of this would be a manager that uses Salesforce. Instead of reaching out to an engineer for them to generate a custom query, they could type it out in natural English, and they would be able to get a response. So previously, there has been some work into semantic parsing over a broad range of languages and domains. For my specific use case, I was really interested to see what the SQL datasets looked like. As you can see here, there's several SQL datasets that have a broad range of different domains and different query complexities. Of these, the one that stood out the most, and I'll cover why in a second, is Spider. Though the problem was that there is no GraphQL datasets. So I wanted to train a model to learn and to create GraphQL. And that would be very difficult without a GraphQL dataset. So I looked into Spider specifically. So Spider is semantic parsing of natural language text to SQL. It has, in the dataset, it has 10,000 questions, around 5,000 unique complex SQL queries, covering 200 different databases with 138 different domains. So each of these queries in the corpus between the train and test or validation data sets, there are different queries and different databases. So for a system to perform well, it must generalize to new queries and new database schemas and new questions, which is a difficult task to cover. This specific task has been tackled for the last few years, and has achieved pretty good results. So here on this slide, you can see what the top 5 ranking leaders in the exact match accuracy look like. And so on the testing set, we can see there's around 60% accuracy on this SQL spider task. So for my task, I had to be able to create a GraphQL data set. And so this spider data set served as a great starting point. First off was being able to convert SQL to GraphQL. I started out not even being able to know if this was possible. And so it took a little bit of time to understand what the tools were and what I could use to accomplish this first task. The two very important tools that I used were Hasura and pgloader. Hasura just generates a GraphQL schema based off of a database, and pgloader converted SQLite to Postgres, and that allowed me to use Hasura on top of it. Then the bulk of the work was converting SQL abstract syntax trees to GraphQL abstract syntax trees, and I'll cover what that is right now. So here's a simple example of a SQL abstract syntax tree to a GraphQL abstract syntax tree. On the left side, we see SQL. So the query right here is select count star from songs. So we take this query, we parse it into a tree. And like I said before, this is a very simple example. Then this tree is then converted to a GraphQL tree, as you can see on the right side. Then that tree is just converted to a raw GraphQL query. Part of generating this data set required the use of validation scripts. And so there was a few things I looked out for in these validation scripts. So when I was verifying this data set, I covered the syntax, making sure that the queries that were formed were actual GraphQL queries. Also validated the syntax against the schema. So making sure that the keywords that were used in the queries itself were valid for the schema that we were looking at. And then I executed those queries against an endpoint to make sure that they were valid. So what this whole process resulted in is that half of the queries were transferred, around half of the queries. So the big problem here, the big obstacle, was that Hasura doesn't include a group by clause. So group by is a clause that's used very often in SQL. And Hasura didn't have a good way to transfer that over. This could have been done manually, but I wasn't able to do that within the time limits of the program. But in the end, I was very confident because of the validation script in the data set. So diving into the details, this looks like 160 schemas across 138 different domains, around 4,300 unique English prompts, and around 2,400 unique GraphQL queries. So after that, the next step was experimenting on that data set and seeing what kind of results I could get. I experimented with a few different models. The ones that stood out the most were BART and T5. So these are 2 different models that other researchers from different research groups have come up with. Both of them are encoder, decoder, transformer models. And they're very similar. Where they vary, though, is that BART is a bidirectional encoder, but both of them are encoder-decoder models and lend themselves very well to translation tasks. So I thought they could lend themselves well to my task as well. So as I mentioned before, the process looks a little bit like this. So we input an English prompt. So in this case, what is the name and date of the song released most recently, concatenated with the GraphQL schema. So it would look a little bit like what you see on the left here. That is passed through to our model T5, and then our output / target is this GraphQL query we see on the right here. And this is just done with an autoregressive objective. Part of this required the use of a validation metric to make sure that my results looked what I expected them to look like. So in this case, I wanted my outputs to look like my targets. The validation metric that I came up with was exact set matching accuracy, What this means is that since I could parse my GraphQL queries, the target and the output, into abstract syntax tree, I could compare those two queries to see how accurate they were. And so since in these abstract syntax trees, the order of the children nodes don't matter. So two trees with a different order of child nodes could be equivalent. So for example, we see these two little trees right here, where on the left side we have a green child node, and then on the right side we have a right green child node. And these two are equivalent queries, and so I wanted to make sure that this validation metric could be able to handle for that. And so a good example of this would be in this query here. The song name and release date could be switched, but the query would still be equivalent. So what did the results look like? With these two models, specifically using T5, which performed the best, I got 46 to 50% exact set matching accuracy on the GraphQL validation data set. This is in comparison to the 20% SQL exact set matching accuracy that I got with these same models. And this is an interesting result for a couple of reasons. This range of 46 to 50% is actually the same model, but the 46% model was just trained on the GraphQL queries. The 50% model was trained on the GraphQL queries and the SQL queries. And for some reason, it was able to perform better. My guess is that that was able to happen because the model learned what keywords were important between schemas. And as I mentioned before, the existing Spider best models got around 65% exact match accuracy, as we can see here. So why did my model perform worse on these? And this is because these models that are in the leaderboard here used specific architecture that was specific only to SQL. So these models here can only produce SQL. They wouldn't be able to produce GraphQL as well, whereas my model was also able to produce SQL and GraphQL. And so this sets it up for future work where we could see potential uses where we could find a way to increase the accuracy of both of them, and maybe even across different query languages as well. As I mentioned before, the dataset, since this dataset was based on the Spider dataset, for a model to perform well, it must be able to generalize well over new schemas and new questions and queries. And so to me, a 50% accuracy says that the model is able to generalize these results pretty well. What I failed to mention a little bit earlier is that this exact set matching accuracy is more of a lower bound because there are multiple queries that could display the same information, but it's a little bit more difficult to be able to parse those trees as well. So what does this look like? It'll be helpful to see a query in action. So here we have a database that we're using. So this database is called Music1, which has information about different music genres and artists. And we can ask a question such as, what is the country of the artist named Enrique? So here we generate a GraphQL query, as we can see below on the left side, and then we can send that query to a server and get a response. And so here we see that our response looks like this. And the answer to the question is the country is USA. Here's another example. And this shows that the model is able to generalize to a different database. So here there's the 160 different databases. And instead of selecting Music1, we're going to look at Flight2, which has information about different airlines and flights. So now we ask a new question, give the airline with the abbreviation UAL. We generate a GraphQL query, and we send that query and get a response. In this case, it says United Airlines. And so this is just a small example of what it can do. In the future, in the next couple of days, I want to release these models and code so that everybody's free to use them and improve them. I've been working on a paper constantly to submit to arXiv, and within this next week, I'll be submitting that as well. And then a little bit longer term, a couple more tasks. So one of them is to add more examples to take advantage of GraphQL. These examples only take advantage of the more simple aspects of GraphQL, but it wouldn't be too difficult to add more complex examples. And another task is to test on an enterprise schema. So Salesforce and GitHub both have GraphQL APIs. And so I'd like to see what kind of results I could get by semantic parsing English to these GraphQL endpoints. And so I just wanted to say thanks specifically to a few communities and people. So I wanted to thank OpenAI for the opportunity to be part of the Scholars Program. I've learned a lot from the people at OpenAI, and I enjoyed having the flexibility to work on this project as well. Also, thanks to Hugging Face and PyTorch Lightning communities, they made themselves very available to me to ask any questions on how to use their tooling. And then I wanted to thank my mentor, Melanie, for taking the time to work with me. And as Sam said, it did feel more like somebody working with me and getting through the more difficult parts of getting into the field. Wanted to thank also Christina and Mariah. They were in charge of the Scholars Program and were very helpful and made themselves very available to all of the scholars whenever we needed any help. And I also just wanted to thank my wife, Noelle, who has been very supportive throughout this whole program. And now I'll open it up for any questions that I can see here on the Q&A. So first question, are your results using models trained from scratch or using fine-tuning pre-trained models? Also, what are the model sizes? So yeah, good question. So the models that I was using were pre-trained on large corpuses, and in the case of T5, for example, it was trained on a corpus that was generated from the internet. And so it learned a lot about language in general. So what I did is fine-tuned those specific models for my specific task in a couple of different ways, but the main one was converting English to GraphQL. And the model sizes, so these models weren't extremely big. I was able to fit both models onto the GPUs that I could run on Google Colab. So Google Colab gives around 16 gigabytes of memory for these models. So I was able to run those perfectly fine on there with some smaller batch sizes. So anybody should be able to do that with a Google account using Google Colab. And the second question is, how often does this model generate syntactically invalid outputs? That's a good question as well. So as I mentioned before, in the validation metric, that validation metric also covers examples that are not valid. And so any example that is invalid would be counted as wrong, right? And so 50% means that 50% were valid and the correct query that I expected. And so 50%, and that also means that 50% were probably not. But that's, so the upper bound of how many syntactically invalid outputs would be 50%. But in practice, when I looked at it, it tended to be a lot smaller than that. It was, I would say something like 5% of the outputs were syntactically invalid. And that's because this model has the flexibility to output different types of query languages. And next question by Mariah is, what was the most challenging part of the project? And I think the most challenging part was definitely converting those SQL queries to GraphQL queries. It was a lot of parsing. It was a lot of using trees and graphs to figure out what the right GraphQL query would be. And so all in all, that process probably took a month by itself to work out. And at the very beginning, I didn't even know if it was possible, but as we realized, about half of the queries were possible to transfer over. Let's see if there's any more. Yes, okay, I have another question from Alec Radford. Do you think general purpose architectures like T5 are sufficient, or is there still a need for domain-specific architectures like the SQL-specific ones you mentioned? Yeah, I've been thinking about this question actually, and I think it depends on the difficulty, because there is a difference between a model that is where the whole model architecture is specifically tied to SQL, and a model where just the output heads are tied to SQL. So if we could, and this could be future work, obviously, if we could replace the SQL head just the SQL head and put a GraphQL head on there, that would be great. But obviously this lends itself to the time required to create those heads. But I think we probably need to explore both a little bit better and compare them. And so I think that's a good place to look in the future. Let's see. And the next question is, how often does the model generate syntactically invalid outputs? I already covered that, probably around 5% of the time. And what's the main metric you've used for evaluating your model? Yeah, that's the metric I mentioned previously, which is the exact set matching accuracy. So I would basically work this way and convert the GraphQL queries into abstract syntax trees, and then compare two trees to each other. And that way I could evaluate my model throughout every epoch. And then from Christina, really cool work. How do you imagine the model architecture to differ for GraphQL as opposed to SQL? Is the problem space different in any way? So yes, the model architecture, I feel like most of the model could remain the same, because these general architectures that as we've seen with other examples, they're able to, we can use them for translation tasks, for task generation, for classification, different things like that. So I feel like my intuition is that, well, where the work will go is in preparing the right types of heads. And what that requires is just somebody who understands how to basically output these abstract syntax trees directly. So I think that these general models will be able to, as long as the general architecture, or in other words, the middle part of the model, is able to understand language, that these models will be able to perform well.